Thank you very much, Janos. As Janos said, I'm a student of Belgrade Topology School, and I would like to stay still a student. And just to explain the title, last week at the same day I gave a talk in Budapest honoring the work of really remarkable mathematician Imre Barany, who had diverse interest in many areas and made the cornerstones of topological combinatorics by his work on Twerberg and Collar-Twerberg theorem and other things. And at that occasion I talk about his work, thinking of him as one of my teachers along the way in my mathematical studies. And today I will talk about my, let's say, current teacher, so I still feel like a pupil. I will talk about a remarkable work of Fred Cohen and how it can be used in diverse applications. So, Shadows of Cohen Vanishing theorem will tell us about a theorem from Springer lecture notes 533. This is a really remarkable book with a lot of materials, and I will pick one really technical result. And please don't be afraid on board when I explain this result, which is rather technical, and then we'll start applying it everywhere we can. So in 1976, the business of introducing homology operations on different kinds of spacings, in particular the spaces with actions of little operides, was on. And Fred Cohen, in his paper, one of two in this Springer lecture notes, in the paper the homology of Cn+1 spaces, introduced homology operations for the spaces with an action of the little cube operides. This really sounds really fancy, but I will forget immediately about everything, and I will only pick up one thing from it. So this is a vanishing theorem that appears on a page 268, and it tells you about the following thing. So if I look at the configuration space of P pairwise distinct points in Rd, and look at its Waller construction with respect to the group ZP, actually I'm even picking the piece from a theorem. My question is, can I understand the spectral sequence of it? Which one? Well, the Serre spectral sequence, because this is a fibration. So the Serre spectral sequence has an E2 term of the following form. This is the E2 term at the point at the ij coordinate is cohomology of BZP with local coefficients in cohomology of the configuration space. And these coefficients are indeed local because fundamental group is ZP of the base space, and it acts non-trivially on the cohomology of the configuration space. This looks already rather ugly, and the question is how to deal with this. Well, why did Fred Cohen use this? Well, he wanted to substitute and solve the problem of non-existence of a nice approximation of B sigma n with using of configuration space. And this was one technical detail he needed, but we will see that this result will imply immense amount of results in various areas of mathematics or combinatorics, let's say. So in order to deal with this, one needs first to understand the local coefficients, in particular the action of ZP group on the cohomology of the configuration space. At that time, the only thing that was available was Fadel-Nurwit base for the homology or cohomology of the configuration space, and a bunch of relations, so-called Young-Baxter relations. And by hand, Fred Cohen computed completely the structure of the action of the ZP on the cohomology of the configuration space. Nowadays, one alternative approach is to use and see the configuration space as a complement of arrangement and apply appropriate equivariant Gorecki-McPherson formula. Doing this, one can state the following theorems. Strangely, this is the theorem I want to talk about. It tells you, as you can see, it's completely technical, out of place, and completely not clear why I would do this. At least when I saw it for the first time. So the E2 term of the spectral sequence is isomorphic to the term in the to the page d minus 1, p minus 1 plus 1. This means that all the differential in between are 0 and everything that was in the E2 page stays alive. And the picture of the E2 page is actually this. That's an this is equal. This tells us that we have only two infinite rows that appear in dimension 0 and in cohomological dimension of the configuration space, which is d minus 1, p minus 1. In the other dimension, where we have a non-trivial cohomology of the configuration space, we have only these short red lines which tell us that the element, non-trivial element, appears only in a 0 column. That's all, and that's the theorem I want to use. If I just for a second think about it, okay, what can I know? This is a fibration and this is a Borel construction of the group of the space with a free group action, and therefore it's homotope equivalent to its quotient. Since configuration space is a finitely dimensional topological space, its quotient is also a finitely dimensional. So in the end, when I compute this spectral sequence, there should not be infinite cohomology anywhere, which means that the row in dimension d minus 1, p minus 1 should vanish, as well as from some point the 0 row. So this already tells us, if we read correctly, that the differential d minus 1, p minus 1 plus 1 is non-trivial, starting from the row in dimension d minus 1, p minus 1 hitting the 0 row. So at one point it's going to wipe everything and my spectral sequence will have basically nothing here, and it will start from here and have nothing more. Fred Cohen immediately applied this result, and as a second part of his theorem he considered the spectral sequence where ZP was substituted with the symmetry group. What is the difference? Well, not much of a difference, only you put everywhere a sigma p, and then you have to compute again. But before you start computing, you can use the result we just explained. Since Zp and P is a prime in our setup, is a P-Silo subgroup, we know that the cohomology of the group restricts injectively the cohomology of the Silo subgroup, which means that my spectral sequence I could write for the symmetric group will inject in this spectral sequence, which means it will have almost the same shape, and it will be exactly these red things. But when you assume that in addition D is at least 3 odd integer, you get a result that the cohomology of the configuration space is an image of the cohomology of the symmetric group. So you can actually say what is the cohomology algebra of the unordered configuration space on p distinct points, and it is a part of the cohomology of the symmetric group. So it suggests this will not be the case, I feel, when D is an even number. Having a classical knowledge of the cohomology of the symmetric group, that it is a tensor product of the exterior algebra and polynomial algebra in one variable when degree of exterior element is 2p minus 3 and the polynomial is 2p minus 1, and they are related as one is a Bokstein of another, you know completely the cohomology of unordered configuration space. At the moment I'm still rather technical, I am getting some pieces of topological informations without any reasons. But I'm just applying my vanishing theorem immediately. The second thing one can deduce almost directly, knowing a few things, is that when P is an odd prime, then the Lusternik-Schnirelmann category of the unordered configuration space is equal to the dimension, cohomological dimension of the unordered configuration space. Of course, today, please have in mind that I'm not giving the best results. I'm just using this theorem and telling you which results you can deduce directly using it. There are other methods to prove other things and extend them, and at the moment I don't want to talk about them. One thing is here, equality is a bit of a lie and overstatement, and it does not follow from the vanishing theorem. What one can prove and how proof of this theorem goes, you can prove a lower bound for the Lusternik-Schnirelmann category by realizing that you can bound back using the spectral sequence you can bound the Lustermann-Schnirelmann category of unordered configuration space by bounding the Lustermann-Schnirelmann category of the unordered configuration space when you quotient out with the cyclic group instead of the symmetric. This is much bigger space, but nevertheless this is a covering of our space, and the Lustermann-Schnirelmann category bounds from below. Then you use this spectral sequence and realize that you have a cohomology element that's non-zero and pulls back from the cohomology group, and this weight gives you the lower bound. So already the spectral sequence gives you this bound. Completely the geometry, if you know what you are doing. So there is not much to do. The thing about equality, well, we proved just using the vanishing theorem, the lower bound, the equality follow from the upper bound, because you can build a model for the unordered configuration space from the equivariant model for the configuration space, which has exactly dimension d minus 1, p minus 1, so the corresponding cell complex for the quotient will be of the same dimension, and you get your theorem. The fourth theorem I want to mention immediately is a theorem of the Borsuk-Ulam type. Still, yes, it's not clear why I'm collecting them. So let P be an odd prime. Actually, this holds also for P a prime. So yes, you can think of P equal to, and let's denote by Vp the subset of Rp of all y's to yp such that they sum up to 0. Symmetric group sigma p acts on Wp by permuting the coordinates, and of course I didn't mention and somehow assumed, sorry for that. The symmetric group acts on the configuration space by permuting the points, and the action is free because we deleted all the diagonals. And the Borsuk-Ulam type theorem tells us that an equivariant map from a configuration space to a sum of VPs cannot exist as long as the sum does not exceed d minus 1 of them. So how would you prove this, and what in hell this has to do with vanishing theorem? Well, whenever you want to prove non-existence of a equivariant map, there is a general framework of Fadel and Husseini, or maybe somebody even before. So I apologize if I forgot about somebody or don't know about previous work, where you say, okay, I have an equivariant map, then I can define a map between their Borel constructions, and I can define the map between their fibrations, and this means that if I can understand one spectral sequence and another spectral sequence, maybe I can decide what is whether such a map on algebraic level can exist. And indeed, we just described the left-hand side spectral sequence, and the right-hand side spectral sequence is simple. It is a sphere with an action. In this case, we will look at a subgroup ZP, cyclic subgroup ZP. It has two non-zero rows, and we exactly know how it behaves. And just comparing these two spectral sequences, we prove this theorem directly using the vanishing theorem. So the vanishing theorem pulls the proof of this result. What would be interesting in a bunch of theorems? Well, we are topologists, we like all of these theorems, but it's always much better to have some motive. Let me tell you about old motive. I mentioned this in many lectures. Let's start with the old motive and then introduce a new one. So a problem, a rather simple and innocent looking problem, was posed by two Indian computer scientists in, well, I think it was 2008 on their web blog, and this is so-called Nandakumar and Ramana-Rao problem. And I first found about this just from Imre Bara in 2008 in Berlin, when he accidentally dropped to my office when I was visiting for 2 days. So it was a lucky coincidence. The problem states the following thing. If you have a convex body in a plane K, and you are given an integer which is at least 2, then you would like to prove that there exists a partition of the plane into convex pieces such that their areas, when intersected with K, are all the same, and also perimeters are the same. Here, when I talk about convex body, well, I can talk about a measure, no problem whatsoever. And when I talk about partition, it's not actually a partition. I believe that the union is a plane, but the pairwise interiors are disjoint, and the measure of the union of pairwise intersection is 0. That's for me a partition. This problem looks rather innocent, and in the case of n equal 2 has a very innocent solution using just intermediate value theorem. Trying to prove this theorem already for n equal 3, it turned out to be quite an achievement, but from this point of view, actually was an exercise, a good exercise and a good start. And I will sketch the proof and to explain how configuration space come into play and why the equivariant map we considered in the on the page before was relevant. Okay. So here's a sketch of a proof. And to begin with, I want somehow to parameterize all the partitions or some good chunk of partitions, convex partitions of the plane, or maybe RD. So instead of working the plane, I can extend my problem just widely. Let's say I'm in RD, I want to have a convex partition such that volumes are the same, d volumes are the same, and additional d minus 1 function has to equalize. That's my problem. So I just extended it. Instead of area and perimeter, I have a volume and additional d minus 1 functions. So I'm going to consider the space of all affine functionals from Rd to R and that this is Rd plus 1. And then for an n-tuple of pairwise distinct affine functionals, I'm going to define a convex partition of a plane in the following way. For an n-tuple of distinct affine functions, I can associate a partition of a Rd such that ki ith piece of a partition is the set of all elements where the ith functional is maximum. These pieces are convex, though some of them can be n. Doing this, having this space of all partitions, I now can define a map that has some nice properties. And this map will be from my configuration space of n points in the affine space to Wn, and so d copies of them, and Wn is the same we had on the previous slide. So I take my functionals, I take my convex partition, and I measure my functions on each piece. What's red there, I just didn't want to write that I normalize. What does this mean? I sum up all the values, divide by n in this case, and subtract from each coordinate, forcing my image to land in Wn. So this map I defined is an equivariant with respect to the actions we talked about, meaning I permute the points functionals in the collection and I permute coordinates in Wn. Very nice function, but what it is good for? If you want to prove such a theorem, you usually start with an assumption that you have a counterexample. So I'm going to assume that I have a bunch of functions f1 to fd. One of them is a measure that give me a counterexample of the theorem. This will mean that my function that I define completely avoids 0 in the image. Therefore, I can map it to the space without 0, then I made the deformation retraction and I land in the sphere of this representation of sigma m. Therefore, I get a question, I get an equivariant map from the configuration space to a sphere I had in the previous slide. And I just know for n prime that such a map cannot exist, and I solve my theorem and resolve it for n a prime. So here's completely unexpected the shadow of the vanishing theorem and the first one to appear. The next one I want to talk about is the last one we found about, and for that let's go maybe, yes, whenever I think about splitting necklaces, I always remember Pick Panther movie and Inspector Clouseau running for that, and let's do this now. The classical theorem of splitting necklace tells you if you have an integer m given and m measures m joules, or necklace with n different joules on a line, on a string, then there exists a convex partition into m plus 1 pieces. Since you're on the line, this means there exist m cuts such that you can distribute these cuts to two thieves such that all of them get a fair share. This is a classical theorem going back to Allen and West and others, which is an application of Borsuk-Ulam theorem, and that has different extensions to high dimensions. So it's a good opportunity to mention Rada and Sinisha had different papers where they extend the notion of multidimensional necklaces. But let me today do something completely different and in the style of a vanishing theorem of Cohen. So for me, necklace will be again a bunch of measures in RD, and now I seek very special partitions, convex partitions, and even convex partitions of a special type. And here's the first one for the one I want to do. So the first line, these are so-called iterated convex partition obtained by successive hyperplane cuts. So what do? I have a knife and I cut somehow by a knife and a hyperplane space into two pieces. Then I look separately pieces and then I continue each of them cutting by a hyperplane. This does not mean that my hyperplane will actually cut the new piece. But now I continue doing this. I allow a cut of a hyperplane at infinity, and therefore cut would be one empty set and the whole space would be the other one. This kind of cutting, it has an analog in the Gromov partition of the space in famous Gromov-Weiss theorem, but has a different flavor because we allow that a hyperplane can vanish to infinity. Having this in mind, the question is, okay, this would be for two thieves. I cut into half and then I will distribute maybe left and right to two different thieves, and then I cut into half or cut somehow, and this partition would work out for two thieves. What about if you have a bunch of thieves doing together? So in this case, the partitions I'm interested in are of the similar flavor. I have a first cut by a hyperplane that cuts my space into two pieces, and then in each piece I apply r-dimensional partition by a convex pieces. In all this business, the first thing you want is to get a reasonable configuration space, the space that describes all these partitions. The partition space described by successive hyperplane cut is a join of spheres, while here we will have a join of configuration spaces. So configuration space is hiding behind this picture. So what is a problem? The problem is to determine the maximal integer m such that for every collection of m measures in the Euclidean space Rd, there exists a convex partition into n pieces such that with the appropriate function of distribution of the pieces, everybody gets the same prescribed amount of measure. Now observe that in this setup, the numbers and parameters n, r, and d are fixed, and we are asking for a maximal measure. Why would we look? So there is a bunch of different applications and extensions of the classical result of Nogalen and West, and why would be this one really interesting? Well, these numbers m, n, r, d hide two classical theorems. The statement that m22 d is equal to d is actually the statement of the ham sandwich theorem, while m of n plus 1, 2, and 1 equal to n is a classical necklace splitting theorem. So answering this question, one would, in one stroke, extend both classical results from mass partition problems. Now the only question is what this has to do anything with our story about configuration spaces. And one hint was on the picture where I had one cut and then I had R pieces on the left and on the right, and since my hyperplane can move to infinity, this looks awfully like a join. Okay? And indeed, this is the case. What we can prove is that under certain conditions, which are that D is an integer, T is an integer, and R is a prime, this MRT, RD is at least rounded up this fraction. And this theorem is a direct consequence, again, after some work, of the vanishing theorem of Cohen. What we asked to get such a theorem is we proved that there is no equivariant map between the join of configuration spaces to, again, a sphere. And since R is a prime, instead of working with a whole symmetric group, we again worked with a cyclic group, and we used the knowledge of the representation of the cohomology of the ordered configuration space with respect to the action of ZR to understand the spectral sequence of the join. So, yes, we did some cutting, and let's play maybe now a billiard. And in the title there is a story about Finsler billiards, and this is a joint work with Sergei Tabachnikov and his student, not actually now a PhD, Mike Harrison, that's going to come very soon. And this is billiard configuration spaces, and it is based on work and ideas also of Roman Karasyov. So what is the question? So before I tell you what's a billiard configuration space, assume that we are in the high space and we have a convex body that's strictly convex, which means on the boundary there is no interval. Why would I like this? Well, if I'm playing billiard, I don't want in the boundary to have something bouncing on the boundary. So I want, let's say, a smooth convex body that's strictly convex, and I want to play billiards. And what I'm interested in is periodic billiard trajectories of the given period, and I want to count them and to estimate them from below. The major breakthrough in applications of topology in this problem were done by Michael Farmer and Sergei Tabachnikov in series of papers with beautiful topological calculations. And here we want to see a vanishing theorem behind one of the results. The framework they developed tell us that we should look at so-called billiard configuration space, and in this case this is the space of all R tuples on the sphere SD-1 Y sphere. I have a convex body in RD, and the boundary where things are bouncing topologically is a sphere. Whether it has this or that shape for our consideration will not matter, so I'm going to concentrate myself on a sphere SD-1. I'm not looking at the classical configuration space, but I look at the billiard configuration space, which means when I hit the ball, it bounces, and which means one after another point cannot be the same, meaning that xi should be equal to, should be different from xi plus 1, assuming that this cyclically goes back, meaning xr is different from x1. Then you have a period trajectory. The question that you want to answer that would estimate the period billiard trajectories are the following two questions. Can you estimate the Lusterman-Schneemann category of the quotient with respect, in this case, ZR, or can you calculate the sum of Betti numbers, for example, cohomological Betti numbers with appropriate coefficients of the unordered billiard space? Here, I'm a bit hiding something. I didn't tell you about geometry where we are playing. If we are playing in Euclidean geometry, the action that appears for the billiard configuration space is not symmetric group. Of course, there is a cyclic shift, but there is also a reflection, and you have a dihedral action. If you introduce the Finslerian geometry, then one thing happens is that you cannot go along the billiard trajectory backwards. So you break the symmetry of going backwards, and then what you are interested in, and you want to distinguish your periodic trajectories is with respect to the group ZR, cyclic group. So instead of looking at the hydral group, now you'll need to look at the cyclic group. Already there is a vibe that the vanishing theorem can help in some way. And for the second, for the understanding of B, we need simply to compute everything. And to do so, you go back first. What can you do? Well, the thing that we assume that R is a prime tells us that the cyclic group action on the billiard configuration space is free. If you don't assume, that's not going to be the case. And the problems start to be rather complicated, and at the moment there is no good idea how to approach it. And since the action is free, the quotient of the genuine quotient is homotopy equivalent to the Borel construction, and therefore instead of looking at the quotient, I can look at the Borel construction, which brings me the fibration with it immediately. Having a fibration, I get immediately a Serre spectral sequence that look now much more complicated than the one we had at the beginning. So the 0 row is missing. Using again the results of Pavle and Tabachenko, you know that these rows in the spectral sequence are non-zero, and they actually bring the whole cohomology of the group ZR. So in pairs, D-2 and D-1 appear, and you want to understand the spectral sequence, for example, to compute all the Betti numbers of the quotient configuration space. How would you do this? Well, you can try immediately, and it's not clear what to do, but then you remember we are talking about vanishing theorem, and the usual classical configuration space is a subset of a cyclic configuration space, and so I am going to embed my configuration space of the Euclidean space to the configuration space of a sphere, and this configuration space will go to the billiard configuration space. All these maps are equivalent with respect to the group action we are considering, and in this case it is a cyclic group action. Having this, we immediately get a map between the Borel constructions and corresponding Borel fibrations. Having a morphism between fibrations gives us again a morphism of spectral sequences, and on the right hand side it is a spectral sequence from the vanishing theorem. And this tells us something about the right hand side spectral sequence. In particular, there is only one fact that we can determine, and that will be enough. We can say from the vanishing theorem that all differentials of the spectral sequence on the left hand side vanish when P is non-negative and S is in the range between 2 and R-1, D-2. Does this tell us something about the spectral sequence and differentials in the fibration too? And the answer is yes. The same holds for the spectral sequence of the associated to the cyclic configuration space. Knowing this fact, you can actually go back to the configuration space we wrote to E2 page and deduce by a simple arguing of and discussing possibilities complete shape of the spectral sequence and actually compute what you have. And for the end, I would like to add one more application which goes back to graph theory. And excuse me if I'm not going to talk about the graphs, I will just pick up the problem from application and tell you about it. So I'm going to talk about the grids on hypersurfaces, and I want to establish an existence of a particular grid on a hypersurface. What I do at this moment is I look at the composition of Euclidean space P into the sum of our Euclidean spaces Rd-1 times Rdk, so I split it into k pieces, and I fix k integers from a1 to ak. I say that the subset a1 times ak is a grid of size a1 to ak if first ai is element of the Euclidean space Rd-1 and the cardinality of ai is a little ai. So what I want to prove is the following theorem, for example. Actually, this is a corollary of a much more general one. If P is a prime and D is 2 times rounded up P minus 1 divided by 4 and then you add 2, then every smooth hypersurface V in RD times RD contains a P times P grid. In particular, every hypersurface in R4 times R4 contains 5 times 5 grid. So how would you prove this? Well, you are going to consider configuration spaces of different cardinalities in Euclidean spaces in play. And you are going to consider their product. This will parameterize all possible grids. Then you are going to use your function that defines your hypersurface, and you are going to define a map to a tensor product of R Euclidean spaces, and then you are going to assume that such a theorem does not hold, knowing that all the grids will avoid a particular subspace, which is in this case a tensor product of diagonals. This will again boil down to a map to a sphere with a particular action, and here the action is a product of symmetric groups. If you assume that all A's are prime, then the action of the group that comes is elementary abelian group Zp to the k, and then you ask a Borsuk-Ulam type question whether there exists an equivalent map from a product of configuration spaces to a sphere of a particular representation. Invoking Fadl-Husseini index theory and vanishing theorem of Cohen, you answer this question and get such a theorem. Therefore, the vanishing theorem of Fred Cohen hides in the constructions of rather abstract algebraic topology objects used for computation of iterated loop spaces, finite iterated loop spaces in this particular case, as modules of Araki, Kudo, Dyer-Lashof operations. But on the other hand, these technical details gives you a bunch of consequences in completely different areas we were not aware of at all. And when I wrote this title, a few hours afterwards, when I sent it to Pavle, I remember a book of Orson Scott Card that wrote in the series of Ender's Games. There was a shadow of the emperor, and I like to think about this theorem that is a guiding theorem that casts a lot of shadows in mathematics. What I didn't tell you today are 2 further applications, and one of them is applications of existence of local K-multiplicities for continuous maps of manifolds, and further on about the existence or non-existence of K-regular complex maps. And the vanishing theorem has a role in some of the answers in these topics also. So I will stop here.
Thank you very much for the nice talk. Any questions? We have plenty of time for questions.
Going back to the billiard configuration spaces, what does the LS category of the orbit space tell you about the number of?
It bounds them from below. Because Fabio and Topachikov proved, and this needs to be proved also for Finsland billiards, that there is bijection between periodic billiard trajectories and critical points of the functional from the configuration space to R, and and they resolve the problems of non-compactness. They are proving that on the small neighborhood around the set that was deleted, the critical points do not contribute to the periodic billiard trajectories. Knowing this fact, then it is a classical knowledge, more or less classical knowledge, that Lustenstein category bounds the number of critical points of a functional, and that's the connection.
Any other question? No more questions, and thanks, Pavle.